Well, hello everyone. We are on notes number 12, cruising along through chapter 2. So today we're looking at what I believe would be section 2.6, and we're going to be reviewing basic functions and talking about their important features, and then we're also going to be looking at something called piecewise functions, and that part of the lesson might be new for you. So that will be a treat. Okay, so we're going to start by talking about your most basic equation of a line. That would be y equals x, or we could call it f of x equals x, and that is also known as the identity function. So the line would have a slope of 1 and a y-intercept of 0, and its domain would be all real numbers, and its range would be all real numbers. So the important things to note about your basic functions would be the domain, the range, kind of what it looks like graphed. Sometimes there are other important points like vertices or intercepts, things like that. Okay, now let's take a look at the squaring function. And the squaring function is just y equals x squared, or f of x equals x squared. So you can square any real number. So that means in the domain we have all real numbers, negative infinity to infinity. But when we square numbers, we're going to either get 0 or a positive, so the range is going to be 0 to infinity. And hopefully you remember what your basic y equals x squared graph looks like. It's a parabola, and it goes through 0, 0, and I'm not going to worry too much about making perfect graphs here. We're just kind of going to do rough sketches. So there's your basic squaring function. It's important to have an idea of your basic functions because one of the next things we do in this unit is we transform them. So we might be shifting them, stretching them, reflecting them, changing them in various ways. And so if you understand the basics and you understand what the transformations do, then it's easy to come up with new graphs. Okay, the next basic function, and I know I'm kind of going through this fast, so please feel free to pause anytime you need to. The next one is being called the cubing function. That would be f of x, or y equals x cubed. And so you can cube any real number, so the domain is going to be negative infinity to infinity. And when you cube a negative number, you get a negative, like negative 2 cubed is negative 8. When you cube a positive number, you get a positive, like 2 cubed is 8. When you cube 0, you get 0. The range is going to be negative infinity to infinity. We could plot some points like 0, 0, 1, 1, because 1 cubed is 1, 2, 8, 2 cubed is 8, negative 1, negative 1, negative 2, negative 8. We end up with this curve that looks kind of like this. Okay, it's not straight and pointy, it's nice and curvy and smooth. Next, we're going to take a look at the square root function. You might not have learned the cubing function in Algebra 2, but you probably saw briefly the square root function, y equals square root of x, or f of x equals square root of x. And you know if you want to get a real output, then you have to square root a positive or 0. So the domain has to be greater than or equal to 0. And when you square root 0, you get 0. When you square root a positive, you get a positive. So the range is 0 to infinity. So we could plot some points. The square root of 0 is 0, so we have 0, 0. The square root of 1 is 1, so we have 1, 1. The square root of 4 is 2, so we have 4, 2. The square root of 9 is 3, etc. We end up with this curve. But it doesn't go on forever. It has an ending point at 0, 0. Okay, let's look at a couple more basic functions. The cube root function would be f of x equals the cube root of x. And just like when you cube a positive, you get a positive. When you cube a negative, you get a negative. It works the same for cube rooting. When you cube root a positive, you get a positive. When you cube root a negative, you get a negative. You can cube root any real number. So the domain is all real numbers, and the range is also all real numbers. The cube root of 0 is 0, so we have the point 0, 0. The cube root of 8 is 2, so we have the point 8, 2. The cube root of 1 is 1. Cube root of negative 1 is negative 1. Cube root of negative 8 is negative 2. So we have a curve like this. And then we're also going to include the absolute value function in our basic functions. So this would be f of x equals the absolute value of x. And you can take the absolute value of any real number, so all real numbers is our domain, but you know that absolute value is distance from 0, and that has to be 0 or positive, so the range is going to be from 0 to infinity. So we have 0, 0, the absolute value of 0 is 0. We have 1, 1, the absolute value of 1 is 1. We have 2, 2, 3, 3, etc. For positive x values, you just get the same number. But if the x values are negative, then say -1, you end up with the absolute value is 1. If x is -2, the absolute value is 2, etc. So you end up with these x values that are negative, and they have positive y values. So we have a v. That should be a nice point at the bottom there. It's a v. Okay, so those are the basics, and the hope would be that if I said, hey, what does the absolute value function look like, that in your brain you would have a picture of it. Or if I said, what does y equals x squared look like, in your brain you would have a picture of it, and then we could work with that picture and do other things to it. Okay, we're moving on to part 2 of our lesson, and what we're going to do is we're going to graph not necessarily an entire function, but we're going to graph a piece of a function, and in some cases multiple pieces of multiple functions. So looking at number 1, we're going to graph f of x equals 2/3 x plus 1. Now we know that's a line, it has a slope of 2/3, it has a y-intercept of 1, but look, we have a restriction here. We're only going to graph it for x values greater than or equal to -1. So what I'm going to do is find the endpoint by taking -1 and plugging it in the function. 2/3 times -1 plus 1, that would give me 1/3. So we're starting at the point -1, 1/3. That's going to be a closed circle. Now I need another point to go through. So I'm going to pick a number that's greater than -1. Suppose I choose 3. I think that would be convenient to multiply by 2/3. So 2/3 times 3 is 2 plus 1 is 3. So this is also going to go through 3, 3. So I'm going to plot that point. So the point -1, 1/3 was the starting point because it said start at -1, and then from that starting point we're going to go through the other point and continue. So we have a piece of a line. We would call that a ray. So we just have one piece of the graph. The idea is we're going to be calling these piecewise functions. Okay, let's try number 2. So this time we're going to graph a piece of f of x equals x squared plus 1. So this is going to be a squaring function, and because of the plus 1 it has been shifted up 1. And so let's go ahead and not plot the whole parabola, but just the piece that goes from -1 to 2. The x values go from -1 to 2. So what we want to do is find one endpoint. So what if x is -1? -1 squared is 1 plus 1 is 2. And what if x is 2? That will be the other endpoint. 2 squared is 4 plus 1 is 5. Okay, now because these are just less than signs and not less than or equal to signs, these dots are going to be open, not closed. So we have an open circle at -1, 2, and we have an open circle at 2, 5. Now, do I want to just connect these with the line? No, I do not, because this is not a linear equation. This is quadratic. We have an x squared in there. So let's think about this. We know what our squaring function looks like. It should look like a parabola, but we've shifted it up 1, so the vertex is going to be at 0, 1, and so it's going to look like this. That's the piece that we want. And what you could do if you didn't know where the vertex was going to be is you could just put some other x values in there and plot those points as well. Okay, so far we've still just seen one piece at a time. What we're going to do next is put a couple pieces together. So this is what you would truly see as a piecewise function. You would see a name for the function like f of x equals, and then you would see an open brace. I don't know why, but for these kinds of functions, we don't close the brace. We just open it. So you see an open brace, you see a list of the functions and their domains, their restrictions. So for this one, we're going to draw a piece of y equals x squared plus 1, so a piece of that parabola, and then we're going to draw a piece of y equals x plus 2, so a piece of that line. Notice that we have these restrictions. So for the top piece, x has to be less than 0. So that's going to be the end point I'm going to take 0, substitute it in, and I get 0 squared plus 1 is 1. Now, that's an open circle because we're not actually including 0. It just says less than. It doesn't say less than or equal to. So that's going to be an open circle. And then I'd like to find another couple of points on the parabola. So how about if I choose -1 for x? Remember to choose something that is less than 0. So if I choose -1 for x, we get -1 squared plus 1, that's 2. So let's graph what we have so far. 0, 1, open circle, -1, 2. And then keep in mind that this parabola would just look like your standard basic function but shifted up 1. So if we were drawing the whole thing, it would look like that. So we're just drawing the left side in this case. Okay? Now for the other piece, we're starting at x equals 0. Putting the 0 in here, 0 plus 2 is 2. Now because of the equal to, the greater than or equal to, that one is going to be a solid circle. And then let's find another point. So suppose we choose x equals 1. 1 plus 2 is 3. So we start at our endpoint, 0, 2, closed circle. We go through 1, 3, and continue on. And that is the other piece. So keep in mind open circles if it just says less than or greater than, closed circles if it says less than or equal to, greater than or equal to. And there will be times when the pieces actually meet. So if your closed circle and your open circle are on the exact same point, then it's just a closed circle. Notice that it does pass the vertical line test. See, if I draw a vertical line anywhere, even here, it only goes through one point. The open circle is not a point. The closed circle is a point. So it is a function. Okay, let's take a look at another one. So this one has 3 pieces. So let's kind of analyze what we've got. So f of x equals 2x plus 4. That's going to be part of a line. F of x equals 5 minus 3x. That's part of another line. And f of x equals x. That's part of another line. Now let's pretend that this was f of x equals, in fact, I'm just going to change the problem. Let's say this was f of x equals 2. Well, that's also a line. It's just a horizontal line. It's constant. Okay, before we graph, this time we're asked to find some function values. So we're asked to find f of -1. So you have to figure out, where do I put -1? Which piece does it fall into? -1 is less than or equal to 0. So plug -1 into the first piece, and we have 2 times -1 plus 4, and that would give us 2. The next one is f of 0. Well, where do I put 0? Uh-oh, I see a 0 here, and I see a 0 here. Which one do I use? It's the one where you have the equals. Okay, so put it in the first piece. 2 times 0 plus 4 is 4. Okay, let's look at the next one. Oops, I shouldn't have erased my 2. Okay. The next one is f of 2. So where do we put that? Well, 2 falls between 0 and 3, so we put that in the middle. So we have 5 minus 3 times 2, and that would be -1. The next one is f of 3. Where do we put that? Oh no, I see a 3 here, I see a 3 here. Which one do I use? Use the one that has the equals on it. So use the bottom piece, and there's no place to put the 3. The answer is just going to be 2. No matter what you plug into that piece, you just get 2. And then f of 4, well, 4 is greater than 3, so we're going to plug that one into the bottom piece as well, and we get 2. Okay, so for the graph, let's go ahead and find a couple points for each piece, like we did on the previous problems. So on the top piece, I'm going to use the endpoint 0, plug 0 in. 2 times 0 plus 4 is 4. Hey, I should have known that. I did that earlier in the problem. That's going to be a closed circle. Now we need a second point, so pick whatever point you want. It should be less than 0, so let's just use the one we found earlier, -1, 2. Okay, so start at the endpoint, 0, 4, go through the other point and keep going. And that's the piece. Now for the middle piece, we're going to use both endpoints 0 and 3. So take 0, plug it in, and you get 5 minus 3 times 0, you get 5. Take 3, plug it in. 5 minus 3 times 3, you get -4. Those are both just less than signs, so those are both going to be open circles. So open circle at 0, 5, open circle at 3, -4, line segment in between. And then for the last piece, take the end point 3, plug it in, we get 2, we already knew that, we did that below. So 3, 2. And then we need a second point, we already found 4, 2 down below. So starting at the end point, go through the other point and keep going. Okay, does it look like a function? If you draw it and it fails a vertical line test, that tells you you did something wrong. Maybe you drew something going the wrong way. Does our graph go through the points that were in the list? Like, does it go through 2, -1? Yep. Okay, great. I think we have one more, but this one we're going to do in reverse. So here we have the graph already. Let's write its piecewise definition. And that means we're going to write the f of x equals something part. So let's look at the piece on the left. That's a constant. It's a horizontal line. It's at a height of 3. That is the line y equals 3. We already have f of x written, so all we need to write is 3. And then we also need to know what x values to use. So it looks like it's starting at x equals -1 and then going to -infinity. So x is less than or equal to -1. And now for the other piece, let's find its equation. So it looks like we have a y-intercept of -1. Looks like we have a slope of 1. So that line would be y equals 1x minus 1. So all we have to write is the x minus 1 part because we already have the f of x equals part. And then this one is going from x equals -1 and off toward positive infinity. Don't include the -1s, so just say x is greater than -1. So that's how we could do that part. Okay, we have a little bit more to do because we're going to look at one of the most famous piecewise functions there is, and it is known as the greatest integer function. The greatest integer function is so special it gets its own notation. You have square brackets around the x. Sometimes you'll see them as double square brackets like this. Sometimes you'll see them as single square brackets. Sometimes you'll see the square brackets that don't have a thing at the top, only at the bottom. So here's what this function does. Each input is rounded down to the greatest integer less than or equal to it. Greatest meaning largest. So let's take some examples. If you had the number 2.3, round it down to the nearest integer, 2. If you had the number 2.9, round it down to the nearest integer, 2. If you had the number 2.99, round it down to the nearest integer, 2. It's almost like everything, let's say you paid, $2.99 for something. Well, how many dollars was it? 2. And then the rest was cents. Let's say you paid $2.30 for something. Well, how many dollars was it? 2. And the rest was just cents. Okay? So it's like we're only talking about the dollar part. If your number was 1.4, it would round down to 1. If your number was 1, it would stay 1. If it's an integer, it stays an integer. So the graph ends up looking like, first of all, every integer maps to itself. So 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, etc. But then everything between 0 and 1 rounds down to 0. Everything between 1 and 2 rounds down to 1. Everything between 2 and 3 rounds down to 2. Everything between 3 and 4 rounds down to 3. So you have these little horizontal line segments because every number in that interval rounds down to the same y value. So that's what the greatest integer function looks like. It's known as a step function, and it's known as the floor function. Everything just rounds down or falls down to the floor. There are other kinds of functions where everything rounds up, and a variety of things like that. So let's end with this problem where we're kind of applying the idea of a step function or a piecewise function to a real-world situation. An express mail company charges $20 for a package weighing up to 2 pounds and $2 for each additional pound or fraction of a pound. Let's let y equals c of x represent the cost to send a package weighing x pounds. Graph the function for x in the interval from 0 to 6. Well, the first thing I want to do actually is just kind of make a table of the weight, x, and the cost, c of x. So if the package weighs up to 2 pounds, so between 0 and 2 pounds, by the way, I'm not going to include 0 because that would just be a package of nothing, then it costs $20. If the package weighs another fraction of a pound, you have to add $2. So between 2 pounds and 3 pounds, $2 more, so $22. Between 3 pounds and 4 pounds, another $2. And we're going to keep going until we get to 6 because it says 0 to 6. So between 4 pounds and 5 pounds, $26, and between 5 pounds and 6 pounds, $28. So now we just have to graph. So on the x-axis, we're going from 0 to 6, so I'll just go by ones. And then on the y-axis, we need to go up to 28. I'll go by 4s. That might not have been the best choice. It might have been a good idea to just make a break in the graph on the y-axis, but oh well, it's okay. So between 0 and 2, the cost is $20. So that would mean open circle on 0, go across till you get to 2. And then between 2 and 3, $22. So right up here, $22, and then between 3 and 4, $24. Between 4 and 5, $26. And between 5 and 6, $28. So most of the steps followed a pattern. They were the same width and the same distance apart, but the first step was different. Okay, here is our assignment, and I really hope you enjoy it.